Hello, welcome to the final webinar in our summer series supporting SAE formula using Hexagon simulation software. My name is Alex Sotmarie, and I'm going to introduce myself and my other speakers for today. First, Joanna Lee Mayer is a business enablement manager. She previously worked as a postdoctoral researcher in academia, specializing in micromechanical modeling of composites and characterization of nonlinear materials. She joined Hexagon about the time that I did last year, and she streamlines business processes, provides training, and supports strategic initiatives. Her job title sounds very businessy, but she really is a very crunchy engineer. Leonard Kruger joins us from Apex Generative Design. He studied he is a solutions engineer in that group. He studied mechanical engineering with a focus on product development and additive manufacturing. He completed his master's degree and joined, again, the generative design department at Hexagon. There, his responsibilities include the execution of benchmarks and technical customer support, as well as support of the development team. And I'm Alex Sotmarie. I'm an academic consulting engineer at Hexagon. So my job is to help students and professors put our software to work, which makes sense. Before this, I was a professor. I was the first mechanical engineering professor at a small liberal arts college in Pennsylvania in the United States. So there I taught almost every mechanical engineering course and came to really focus on computing and design. And so it was logical for me to move to Hexagon. And so now I do things like consult for professors, develop curriculum for classrooms, I make instructional YouTube videos, and I organized this webinar series. Okay, here's what we're going to talk about today. First, I'll give an overview of structures for Formula SAE using Hexagon software. Then I will show a demo of analysis of an upright, or sometimes called a wheel carrier. And then Joanna will show analysis of a composite panel. After that, Leonard will show about using Apex Generative Design to have the computer actually generate the geometry of an upright for you based on the requirements that you supply. He'll also talk about some other aspects of generative design. I think it's a very interesting topic. Finally, I'll show you how you can access Hexagon software and follow up, go deeper with, learning how to use our software to become more successful in Formula. And I really hope that this actually helps you kickstart your career. And of course, we'll have time at the end for questions. So these are some of our customers that use our software. And actually, I know that this list is technically just people who use one of our programs, MSC Apex, but there is a lot of overlap between that customer base and who uses our software more broadly. Hexagon simulation software has very strong ties to aerospace, and our flagship simulation product is called Nastran, and that Nastran is from NASA. Nastran is short for NASA Structural Analysis. Of course, it's come to find use very far outside of aerospace. It is used a lot in the automotive industry. Here are just a few of the companies that use it, but I can tell you that many more are also customers of us using Nastran in particular. And our software is not just limited for the aerospace and auto industries. One of my favorite case studies is how Apex was used for designing the Giant Magellan Telescope in the Atacama Desert in Chile. Our software is used in shipbuilding design, heavy industries, so think large construction equipment. So we really serve a very broad customer base, but I'm assuming that a lot of the people who are viewing this webinar are going to be really interested in the automotive industry in particular. And if you want to learn automotive software, we are a good company to be talking with. So here are some of the packages that we offer to students, some of the software that we offer to students for free as part of our student competition bundle. And that's shown in this green rectangle here. In the blue rectangle, which overlaps considerably, we have our software for structures simulation with finite element analysis. We previously had 3 webinars on atoms, 1 on Romax and 1 on Cradle, and you can find those easily on our YouTube channel or on the Sim Companion page, the website that we have set aside for this webinar series. I'll be sure to share that with you later. We have another package, Actran, which is used in acoustics. I haven't seen acoustics modeling being done a whole lot yet in Formula, but I also have heard that some of the vehicles are very loud, especially if they're adding like active downforce, and so Actran should be used more in formula. Our focus today is structures simulation. Now, the one product that you don't actually get as part of the student competition bundle is called SAE Fatigue, which, as I understand it, can take simulation output and then actually do some crunching on that to figure out what kind of fatigue failures would be likely. Like I said earlier, our flagship structure software for finite element analysis is MSC Nastran. And again, this is a very powerful finite element solver. When you are using Nastran, you're typically not looking at Nastran, you're looking at a pre or post processor like MSC Apex and Patran. And these days, I would say Apex is probably the one that you want to start with. Patran can do very similar jobs. It's more a legacy piece of software. I would say that Apex is like an SUV and Patran is built like a pickup truck. I know which one I would want to use to get around town, but either one will do the job. There is Dytran, which is typically used for crash simulations or other things where you have extremely fast, very rapid deformations occurring. We have Mark, which is very powerful for nonlinear structural analysis. Now, MSC Nastran is good, and it's actually getting better and better at doing nonlinear analysis. But so Mark is fantastic for simulating machining processes where chips are undergoing really great deformations and flaking off. It can handle that kind of extreme deformation. DigiMat is good for materials modeling. For example, you can have a complicated composite setup and figure out what kind of bulk mechanical properties you would then import into a larger finite element model. And finally, I would mention MSC Apex Generative Design, which, despite having a name that's similar to Apex and a user interface where there is a lot of overlap, the job that we're doing with it is pretty different. With Apex, we would say, here's our geometry, here are the loads that are being applied to it. Is it going to fail? With Apex Generative Design, we would say, here are the loads, here's the general space that we want the geometry to be in, here's what the failure criteria are that we're concerned about. Computer, you figure out what geometry to use. For our discussion today, Joanna and I are going to be focusing on MSC Apex and MSC Nastran, and Lennart is going to be focusing on MSC Apex Generative Design. I'm about to show you my demo for analysis of an upright. Our engineering goals for this are to reduce weight and really reduce unsprung mass. You can save a little bit on the weight of the vehicle by streamlining an upright, but really a lot of the benefit for being meticulous in your design of an upright is to reduce unsprung mass, which gives better vehicle dynamics performance typically. To be able to meet those overall engineering goals, we have simulation objectives. We need to be able to predict the stress and deflection on the part to make sure that it's not going to fail. Now I'm going to give an outline of the information that I'm going to enter into Apex to set up the model, and then I'll actually take you step by step through how to do these things. So first, I'm going to be using a uniform 2mm quadratic tet mesh. Oh, and I should pause at this point and say, this is going to be a good explanation for getting you started with simulation with Apex, but if you've never done finite element analysis before, that's something where really having a college course in it would be very beneficial. You should at least consider doing some kind of training, getting mentoring to make sure that you're using it responsibly. So if you don't know what a tet mesh is, I'm sorry, today is not the day for me to be able to get the details of that for you. But if you want to see how to apply one to a model, that's what we're here for today. I'll say for this geometry, 2mm is going to be prohibitively coarse for being able to get realistic results. I will actually show results that have been generated with a 1mm mesh, and for this geometry, that's going to be more reliable. We'll find out that there's a problem with the mesh as we generate, and so I'll show you one geometry cleanup feature in Apex. And actually, one of the things for which Apex is just best in class is geometry cleanup and meshing. So you're only going to be able to get a sampling of the thing that Apex is really, really good at, unfortunately. Still, I think geometry cleanup in Apex is really, really fun. Then I'll show you how the model is constrained at this bore here in the center. And now's as good a time as any for me to tell you a little about the overall geometry of the upright. I came up with this model myself just as a demonstration. It's not intended to be a great upright. This is an example of a rough draft that you would feed into a finite element package, and then from there see where it's too weak, figure out how to make it stronger, or figure out where your factor of safety is way higher than you need, and maybe you can, cut some holes in it so that you'll save on weight. I would also say that the details of this are based on the case study that Lennart will discuss later for an upright specifically for an EV designed for the formula team at the University of Paderborn. And for that, they didn't just have an axle going through the upright, but it was the carrier for the electric motor and for the planetary gearbox. And so this bore is much larger than you would be used to seeing. Here's the mounting point for the lower control arm. So a bolt would pass through those two holes and the lower control arm would attach to that. Here are the mounting points for the brakes and the mounting points for the steering arm. There's actually two mounting points so that people could try out different configurations and see what works best in practice. Up here, we're not actually showing the direct attachment point for the upper control arm or its bolt. That's something that would be held on by an additional bracket, and then that bracket would relay loads. And for our purposes, it's going to be a fine assumption to suppose that those loads are being transmitted through these two bolt holes up here. The loads that will apply in the first demo that I show you, we'll just have these two forces being applied at the upper and lower control arms, and these forces are going to be having X, Y, and Z components. The material that we use will be aluminum, and I'm using notation here that is how it's normally written up in Nastran. Okay, so let me take you to Apex. First, I'm going to actually save the file. So I created a new file. I'm going to save it right away before I make any mistakes. We'll call this upright demo setup 5. I will import my geometry. One of the most common questions that I get from students is, will I be able to bring my CAD file into Apex? And the answer is almost certainly yes. You see that we support SolidWorks, Inventor, Cassia, ProE, NX. We also support formats like Parasolid, Step, IGES, and those are designed to be more vendor neutral and interoperable. In this case, I found that using Parasolid was a great way for me to get my CAD file in. So here's my upright. Let's mesh it. I'm going to Meshing, and I will click Solid Mesh. Again, I'm using a relatively coarse 2mm mesh, and I've selected tetrahedrons using quadratic elements. You generally want to avoid linear tet elements. I'm going to click on the part, and it automatically meshed. Apex is generally pretty eager to get to work for you, so if a tool is highlighted like this, that means that it's in automatic tool execution mode. If I had that disabled, I would have clicked on the part, and it wouldn't have meshed right away. I would have then needed to click the middle mouse button or click the apply button. I'm going to leave this on though. Okay, so the part is meshed. Let's see how good the mesh is. We have a tool here for visualizing element quality. And there are a lot of possible metrics we could use for element quality. And what Apex does by default is it shows you an aggregate of many of these different metrics. But if you really wanted to go deep on one of them, you could. Overall, a higher quality element for a tet mesh is going to be closer to a perfectly regular tetrahedron. By default, Apex wants to show you the element quality for 2D elements. We don't have any of those in our model, so we're going to go to 3D. This looks like we started out with a pretty good mesh, that we do have 88 bad elements, at least we don't have any that are invalid, but those are 88 compared to 80,000 good elements. So overall, we're in pretty good shape. We wouldn't want to trust the results too much, especially near those bad elements. So let's see if we can get fewer of them. I'm going to right click on that and click show only. So now we're only seeing the bad elements. We see little speckles all over the place. It's hard to figure out what the pattern is to the problems with this mesh. I'm going to right click on Bad Now, and this will show a wireframe of our geometry. In general, what we see is, it's impossible to generate a perfect mesh. We wind up with a couple of bad elements just kind of scattered here and there. And what I'm doing right now is just changing what things my mouse is selecting so the part doesn't highlight in a clumsy way. Okay. We also see like I should probably have a fillet down there, and I don't, and so it's hard for the mesh to be very smooth right there. I should definitely have a fillet at that seam there. And I would want to go change those in my CAD model, ideally, although you actually can edit your geometry in Apex really easily to add in fillets. What I see here is I have a seam of elements, and they are really thin and flat. So these are really pretty awful elements. Where did they come from? Well, the issue is that I actually have two edges that are very close to each other, one here and one here. And by default, if you have an edge in your geometry, Apex is going to try to make any elements near that edge actually be flush with it rather than spanning over it. So Apex is cramming these really flat elements in between these two edges. But it's easy for us to make that behavior change. We can suppress those edges. So I went into Geometry Edit, and you see there's more than a dozen tools here that are very powerful. There are some things where you can, just with a couple of clicks, remove all of the stray points or stray curves in your model to clean it up. It's very easy to delete all of the fillets from your model if that's something that you need to do. Here I'm going to use the Suppress tool, and I've put this in manual mode. I'm going to select this edge, and now click the middle mouse button. Again, Apex is generally eager to work for you, and so after I change this aspect of the geometry, I don't need to do anything for the mesh to update. And we see right away that our element quality issues here are resolved. Now our element quality is not great right at this fillet, or rather where a fillet should be, but that's something for the CAD operator to fix later. Okay, let's get ready to set up a simulation. First, I'm going to constrain the bore of this. So we can set loads and constraints using this Loads and Boundary Conditions tool. And I'll click Constraint. A lot of Apex tools have something called a pick filter on the left. So if I wanted to select the entire body, or if I wanted to select a single vertex, I could do that. In this case, I want to select this interface. There are a few different types of constraints that we could use. I'm going to use a clamped constraint. So I click there, and because the tool was in automatic mode, it automatically applied. Now I'm going to apply forces. First, I'll apply a force at the upper control arm. I actually have the numbers already entered in there for that. Again, I have faces selected here. Now, because I want the load to be split evenly across those two holes, it's going to be really important for me to have automatic mode turned off so that Apex will wait for me to select both of those holes before proceeding. By default, Apex applies loads to nodes. That is not what you want almost all of the time with solid elements. And for more details on that, I've actually made a YouTube video all about how to apply loads to solid elements using Apex and Nastran. I'll share a video about that later in the chat. Or if you're watching this on YouTube, it should be in the description. So that's what direct would do. That is really important for some jobs. That's not what we want here. Instead, we're going to use a remote load. And we could use that as something that is rigid or compliant. Rigid would mean we're basically creating a virtual part that's perfectly rigid, that is glued to these bolt holes, but that adds rigidity to our model in a way that's fictitious. There can be some problems with using a compliant load application, but those are not going to be an issue for us. I've already checked and made sure that this is going to be fine. It's not going to mess up our results. In Apex, the term for this kind of thing is called discrete ties. In Nastran, it's called a rigid body element, or RBE2. So RBE2 or RBE3 is what we're dealing with. We're doing RBE3s. I'm going to click on this hole and now click the middle mouse button. So Apex is trying to generate an RBE3. It's saying I'm going to put the loads onto the nodes inside of those bolt holes. But where's the force going to be applied? Well, let's try and get it to the centroid of those two bolt holes. You need to be really careful where you click when you're generating an RBE or a discrete ties. So if you don't have the pick filter set, you could accidentally have it really go to all kinds of points. But this filter here for average points gets you at the centroid of the nodes that you're wanting to load. And I think that's the best one for general purposes. Now I'm going to click the middle mouse button. There we go. And now we have our load applied. If I rotate, you can see that we have a force vector there. It's pushing down. So that's the weight of the vehicle acting down on the upper control arm, or at the upper control arm mounting point. I'm going to apply another load down at the lower control arm, down here. So the force there to apply is 4 newtons in the x direction, 93 in the y, and -9 in the z. So I click this and that bolt hole, I middle click, and then I click the centroid, and I middle click. So both of those loads are created. Oh, over here is something called the model browser. So this shows us all the parts of our model. Like whoever made this CAD model didn't come up with a great name for it, but by clicking here, we can get it renamed. Let's just call that upright. Here we have the constraints. And here we can mouse over. We should be able to see the loads highlighted. So you see how this force vector here, it's a little bit difficult to see, but that force vector down there got highlighted. Or when I mouse over the constraint gets highlighted. For documentation purposes, it can be very helpful to label the constraints and the loads in a meaningful way. You'll see that in a demo that I'll show later. Now we need to apply material properties to this part. And I've seen people get tripped up with that. There are really 3 steps to applying material properties in Apex. First, we have to enter the raw material properties. So what are the material properties of aluminum? 70 gigapascals. And I should say my unit system here is newtons, kilograms, millimeters, seconds. And so our stress unit would be megapascals. We've got a Poisson ratio of 0.33 and a density of 2.7. And I can write E-6 to say 10 to the -6. So, and let's name this material as aluminum. Now the part is not yet aluminum. We've done one step of the process. Now we need to make a 3D element property. And a 3D element property combines the actual material properties with how they would behave as a 3D solid element in a finite element model. So for material ID, I can click here to bring in aluminum, and I can name this property aluminum 3D. That was step 2. Step 3 is to actually assign this 3D element property to all of the elements in this part of the model. So I click there, and I need to click this button, click the part, and this part is now aluminum. And we can check and see that by mousing over, and we see aluminum. We're about to create a simulation scenario. I'm using something called the new scenarios in Apex, and to apply multiple loads or multiple constraints, you need to do something called a load or constraint combination. We do not actually need a constraint combination because we only have one constraint, but because we have 2 loads, we will need a load combination. And we can call this load case static. And I just use checkboxes here to select the loads that I think Apex should consider. This is really great if you want to eventually model multiple different types of loads. So maybe we want to see what happens if we have static loading and braking loading and run all of those simulations at the same time. I'm going to click the green check mark to apply, and now this load combination is created. I click Study. I'm going to create a scenario. This is a job for Apex. And you can pick different types like buckling, dynamic responses, nonlinear. We're going to just do linear. I click OK. I need to tell Apex that I'm dealing with this geometry, this upright. So I right-click on Model Representation and click Associate Model Rep. I double-click on the part and click OK. If I wanted to simulate multiple load cases, I could right-click on Load Cases and click Add Subcase. And then I can click here, and I could enter in a name for that case. One load case was already generated for me by default. Then I come to Loads, Constraints, and Initial Conditions to be able to say which constraints are we dealing with and which loads. On the left-hand side of this menu, we have a tree. So we could apply some of these at the overall scenario level, and then we could apply, for example, different loads for each loading situation. So because I would want the same constraint for all of the conceivable loadings for this part, I could do constraints and pick this single point constraint here. And then for this single static load case, I can click on that, click static loads. And you see how I have radio buttons here. I could pick one force, the other, or because I generated a load combination, the combination. Well, that's what I want. I click OK now. I can right-click on the scenario and click Place an Analysis Scene. Apex will do some checks just to make sure that the model is ready to run. It says it's ready to run, and I could click on the yellow runner to run the simulation. That would take a couple of minutes, so let me show you one that I already did before we got to talking today. This is a model that's a little bit more sophisticated. It's the same upright geometry, but let me point out a couple things. One is that the mesh is significantly finer. It's 1 millimeter instead of 2 millimeter. And that makes it so that across this face here, I have about 3 elements going across. This is still looking a little bit coarser than I would like for practical purposes, but it'll do. This is on the coarse end of what would be acceptable. There are some parts here for which the mesh really is honestly still a little bit too coarse, but this is much better than what I showed you before. You can see that I have many more loads here and 5 distinct load combinations that combine those different loads. So different cases for static loading, braking, accelerating or braking while cornering, and then simply doing cornering right in the middle of that operation. Other than that, the simulation is very similar to the one that I already showed you. Under Study, I have these different load cases, and I could rename the load cases to actually match those load combinations. This simulation was already run, so I can simply click this post-processing button to look at the results. Okay, I am using Shift in the middle button to pan my view in Apex, and the scroll wheel to zoom in a little bit. So here is my upright after the simulation has completed. And if you look closely, it has deformed relative to what its actual geometry would be. I'm going to click this button, and you see the deformation is turned off. I turn it back on, and we see it deformed. This is a really exaggerated view. I can click here. And this would take us back to the true deformed scaling. But if I compare that to, again, no deformation, it's a very small difference. So when we're doing finite element post-processing, we typically use an exaggerated relative scaling, especially if we're looking at failure of metals that aren't going to deform by a great extent before they fail. If I want to know what the stresses are, I can create what's called a fringe plot. So I click on fringe. And by default, Apex shows me what are called von Mises stresses. To control what I see, I can click this expander here. I can change what I'm looking at, like stress or displacements using this menu. I could change the type of quantity that I'm looking at, like von Mises stress, which is what we typically use in finite element analysis to lump together different stress components like X and Y and shear stress. or we could use the maximum shear stress, which is what you would get from Moore's circle in a solid mechanics course. I'll switch back to von Mises. There are many other options here, of course. Let's say that I don't want the stress to go higher than 150 megapascals. I can click right here and enter the upper limit, and now any portion of the model that is red would be concerning to me. I can inspect exact values at different points in the structure using this probe tool up here. I'm going to click fringe so that when I mouse over, the white number that we see is the element or the node ID, and the yellow number that we see, 160.75, is the stress value at that point. So I'm pretty concerned about this part of the upright. It should really be thickened up. I can double click on these other load cases to switch between them. So here's what we see in the braking scenario. I can turn my fringe plot back on. Oh, it's already on. Great. Oh, wow. Yikes. This upright really needs to have its geometry changed so that it can be much more capable of handling the loads that we're going to place it under. So a designer, or an analyst rather, would look through all of the different load cases, see all of the parts where all the points on the part where the structure is unacceptable, and then come up with ways to improve the geometry. They might go back and do that themselves in CAD or give notes to the CAD analyst. So overall, I've shown you in about half an hour the total workflow for going from having a raw geometry to having analysis results in Apex, and again, using Nastran as the solver. Next, Joanna is going to show you how to do this kind of analysis, but for composite materials.
Thank you so much, Alex.
Okay, thank you, Joanna.
So I'm just going to follow on from Alex's demonstration on showing you how you can use MSC Apex for analyzing stresses and your components. What I want to do is, I understand for part of the lightweighting for your car designs is the use of composites. And I want to show you how MSC Apex can help you do that. One thing I understand in particular is if you want to use a composite for your monocoque, for your chassis design, you need to prove that your composite that you've designed, it meets certain material requirements. So the bending stiffness and the UTS, and that's what I'll show you today, how to set up a virtual 3-point bend test for a Honeycomb composite. So here we have this useful custom tool that can help you draw the honeycomb geometry, and it saves you having to draw it manually. So if I create a honeycomb with a 6.4 cell radius, I'll have a 10 millimeter cell height, and I want 27 cells. You can change the upper panel thickness. Here we'll say it's 1 millimeter. And we'll say the honeycomb thickness itself is 0.7 millimeter. And if you click OK, you'll see that Apex will automatically draw that geometry for you. I set that and then I exit here now. You can see the panel has been drawn for me with the top and bottom layers. And what I can do is here I can turn on this thickness tool, and you'll be able to see the thicknesses of the respective parts. So the honeycomb, I have 0.7 millimeters, and then in this top and bottom panel, it's red color, so it's 1 millimeter. So to save time, I have set up this honeycomb panel. So the honeycomb panel tool helps you create a honeycomb geometry with the top and bottom panel that is and you can assign a material property to it. But instead, in this demonstration, what I want to show you is a honeycomb panel with a core that is aluminium, and then a top and bottom panel that is of a composite layup. So I've here you can see I've got a top and bottom surface, and I can turn them off And you can see here, I have that honeycomb layer, a see-through honeycomb layer without the skin. And then on top of that, I would have these top and bottom skin. So then I can do my layup in a minute and assign composite properties to it. Here I have my constraints because it's a 3-point bend test. So I choose a better view here. You can see at the bottom, I have the simple support here, and then another one on the other side. And then mid-span, I have my displacement load. So I have an enforced motion here of 3 millimeters. For material properties, I have aluminium. And the aluminium has elastic plastic properties assigned to it. So I've included that using this table here. And then for the pre-preg, I have chosen a shell orthotropic material. You can see here I've inputted the modulus, Poisson's ratio, and the shear properties. And on top of that, I have the failure model. As composites fail, they lose the stiffness immediately. So I've chosen an immediate stiffness degradation, and I've used the Hoffman criteria for the failure. So here I put in the allowable tensile stress and compressive stress in the different directions, and for shear, and I've enabled progressive failure. So now that I have the material properties, what I'll do is I'll first create a sheet. And I'll select the material pre-preg, which I created earlier. I'll specify the thickness of the sheet to be 0.25 millimeters. And then if I click create stack, I can then select that sheet. And before I do that, I'll select symmetric. And I want an odd symmetry, so then it's an alternating layer. So I'll select the first layer. I want to use the sheet 1, which I defined earlier. So you can see the materials pre-preg and it's 0.25 millimeters. And I will input the angle to be 0. And then I'll add another layer, 45 degrees. And then here, and I can build up my layer. There you go. I have 7 sheets, and that's my stack. And now I assign that stack to the panels. So in here, I'll select the surface. So assign this to the top surface. And then you can see the pink arrow showing the build direction. And I want it to build from the surface of the honeycomb up and away from the honeycomb. So here I'll choose the stack 1 to make my panel. And I want a 0 angle. And then I choose this. And then there you go. You can see that it's populated my panel with the stack that I created earlier with the 7 layers, the material pre-preg, thickness, and the angles that I specified. And I do the same for the bottom surface. And it's correctly selected the build direction. As you can see, it's going down away from the honeycomb. Select stack and angle 0, add that to the surface. And there you go. I've also created this panel. And if at any time when you're building your model, you want to have a look at what composite layup you've assigned to a certain surface, what you can do is you can use this core sample tool, and then you click on the surface. And it will show you what's in there, and you can look at each individual layer individually. So apply 1, 2, 3, 4, 5, 6, 7, and the angles and the thicknesses. So once you've done that, you run the analysis, and I've got an analysis which I've pre-run before, and I wanted to show how you'd look at it in post-processing and get the information you need for comparison with the steel tube material properties that you need to do. So here you can see I've selected one of my analysis that's called 3-point bend honeycomb 25. I'll select load case 1, which gives me the results of the displacement that I've applied. What you can do is click stress for the fringe plot. And now we're on time 0, but what we want to do is see the stress state at the end where it's applied 3 millimeters of displacement. So here you go, and you can separate the components. So we can select the honeycomb, and you can look at the stresses inside the honeycomb and see what's happening. And you can go through each time step one by one and see that stress developing as it is being deformed up to the end. And then for the composite plies, you select to look at the composite ply stress. And then if you expand this dialog box here, you can select to look at maximum principal stress. I forgot to bring my panels back. There you go. So you can look at each layer individually. And you can see the stresses, the stress stage of each layer is slightly different. And what you can also do is select all of the layers and envelope the result and look at the maximum or the average. So I suppose the most important and interesting point for you, if you're setting this up as a virtual test for designing your composite panels, is that you need to get the maximum bending. You need to get the ultimate tensile strength and also the bending stiffness from this panel. So here you can use this probe tool, and you select the reference node here in the middle, and you click OK. And what you can do is plot the reaction force and the translation. And you can see here that 3 millimeter displacement has been applied linearly. And then corresponding to that displacement, this is the stress state. So you can see it, this is the linear region, and then it goes into the plastic deformation, and then it undergoes damage. So here you extract the bending stiffness by getting the force and dividing that by the displacement. And I think for this panel, it comes to it came to 40 meganewtons per meter, which is above what it is for steel, which is 1.2 times 10 to the 6. I think that was the quote. And the ultimate tensile stress you can see here is above, just above 40 kilonewtons. So if you look at the results here, you can see that I have run this analysis multiple times. So what is very handy when it comes to using Apex to explore the design of your composites is that you can easily go back and change any of those properties. You can change the thickness of your sheets, you can change the properties of your prepreg or your aluminium core and replace it. And then rerun the analysis, and you can see and keep all your results here and look at them and compare them. So here is another analysis I've run for the same panel, but with slightly different material properties. And you can see the animation here of that panel being bent. If you slow this animation down, that's too fast. You can see that test going on. So changing the material properties and rerunning it is quite straightforward. All you do is exit post-processing, come back out of it. You can click on your panel and you can look at these properties and change it. So if I want to change that thickness now, I've been playing around with this, I can change it to 1 millimeter. And that's all I have to show you. Thank you so much.
Thanks, Joanna. Then I think it's my turn. Let me share my presentation. So hi everyone, I'm Lennart from the Generative Design team. And in the next 10 to 50 minutes, I want to show you of what MSC Apex Generative Design is capable of. So let's jump into the slides. So generative design is actually the next step in the evolution of part design. So back in the days, we were used to draw mechanical components by hand on paper. And then we had the evolution with the digitalization and CAD software. So we can now draw parts on a PC, and we can do versioning and assemblies and so on and so on. But these parts are still manually created by a human. And then the next step is generative design, where a software or an algorithm creates the part. So let's jump to a first example here. This is the wheel carrier of the Formula Student Racing team of the University of Paderborn from 2019. And here on the left side, we can see such an run-through of a generative design simulation. So we start with the so-called design space. And then over the time, we do a lot of FE analysis. So several iterations are calculated for the loading conditions. And based on the calculated stresses, the optimization algorithm decides where to place the material. And at the end, we have a final design. And this here on the right side is the manufactured part. This was made out of aluminum and with an additive manufacturing process. And this one was used from 2019 on for several seasons in the racing series. What is the big difference to classic topology optimization? So topology optimization exists since several decades, but this process from the optimization to a final part can be quite lengthy. So a classic topology optimization needs to be set up by an expert who knows how to mesh a part correctly, to set up the optimization constraints correctly, and you can run the optimization. And then you need an expert who can interpret the results, because the results from a classic topology optimization aren't always clear or straightforward. So sometimes we have some examples here on top. Sometimes there are structures like this. You do not know if this strut should be part of the final design or not. Sometimes you do not know if this should be a shell or several thin struts. And as output, you just get your elements back. And this is, of course, a rough surface. And because of this, you need to switch to a different software and maybe to a different human person who then tries to create out of this optimization result a new CAD file or geometry, maybe with some smoothing and so on, or sometimes also a complete reconstruction in the CAD software to get as close as possible to this optimization result. And then you need to go for verification once again in a different software done by an expert. And MSC Apex Generative Design tries to shorten this workflow. So now you can do all of this in one software. You do not have to be an expert. You can set your optimization. You do not have to mesh it. Then you can run it automatically. And at the end, you get CAD geometry back to bring it back to your CAD file system or to verification or whatever. Let's have a closer look at this case study here. Once again, a wheel carrier, but now from the year 2021. And this is quite interesting one because the target here was to create a wheel carrier where the electric drivetrain is integrated. So we need space for an electric motor, we need space for a gearbox, and of course this part should be as stiff as possible and as lightweight as possible. And this was all done with MSC Apex Generative Design. Here in this explosion animation, we can see the newly designed wheel carrier. Once again, this is made for additive manufacturing out of aluminum. In the optimization process, you can set up a target stress. In this case, it's a little bit above the fatigue strength of aluminum. And inside this wheel carrier, the electric motor is placed. And on the outside, we have this planetary gearbox. And we can see it here in the assembled state. So down or on the back here is the wheel carrier. Then we have the braking caliper attached to it, the brake disc on, and the planetary gearbox on the outside. And from the side here is the wheel mounted. And this is a nice design, which is really lightweight integrates the other designs and is loaded beneath fatigue strengths. And this part here was used also for the last seasons of racing. Right now, generative design is a perfect fit for additive manufacturing because a lot of the designs are quite complex and additive manufacturing is able to produce them. But we are also able to create designs for casting, so more conventional looking designs. And in the future, we also want to go for designs for milling or machining. And now let's have a look at how to use MSC Apex Generative Design. Unfortunately, this is not a part from racing. This is a part from the automation industry. This is a bottle gripper here as an example. So this gripper has to grab the bottles from the assembly line. And now let's have a look at the video here, which shows a complete workflow from the beginning to the end in MSC Apex Generative Design. So the graphical user interface is the same as you already have seen from Joanna and Alex, but this is now for generative design. And we now normally start by importing a CAD file. This is our design space. This is the starting point of the optimization and also indicates where the material can be placed. And then, of course, we have to create boundary conditions. So in this case, we have some fixations or displacement constraints where the bolts go through at the bottom, and we are applying remote loads which simulate the bottle under moving. And we are applying some gravity loads or acceleration when the gripper moves. Then here in the next step, we select the interfaces. So interfaces are functional surfaces, and these will be also part at the final design at the end. And here in this step, we do exactly the same as Alex already did. We're setting up some load cases. So in this case, it's just the movement in X, Y, and Z direction of the gripper. And then we are ready to start the optimization. We do have something like a live post-processing. So you see every iteration which is calculated. So you can see the first iteration after a few seconds. And we start with a real coarse resolution, and then over time, the resolution gets finer and finer. And at the end, we have a final design, a suitable design, which can be more or less directly used, at least for additive manufacturing. So no disconnected struts, no unclear structures. And with one click, we can go back to a CAD file, this step right here. And we also automatically attaching back the boundary conditions, and then we can easily switch to Apex for Nastran. This video is a little bit older. There we had to really switch the software. Nowadays you can just do it with one click the options to switch the mission from generative design to Nastran, and then you have your part in the graphical user interface for the Nastran reanalysis. And here you can remesh it with a tetraeder element. Then you can check your element quality like Alex did, and your loads are already attached to it. Just a quick check here. And then we can set up our reanalysis scenario. Once again, we have to set up our load cases here, and then we can run the verification, the simulation in MSC Nastran. So here we go. And as we already have seen, we now can observe the stresses of the part, the Vermeer stress or max principal stress, and so on. We can check once again if we have some areas which exceed the stress, the desired stress. In most cases, you want to be below the fatigue strength of the part and maybe also including a safety factor. And you can check the displacement of your part under loading condition and the movement. All right, if you want to have a look at the case study of the wheel carrier, you can go to our website. And if you want to use MSC Apex Generative Design, we also have a help website with tutorials and demos and a lot of explanations of all the optimization parameters and so on. Okay, thanks for your attention, and back to Alex.
Thanks, Leonard, and thanks, Joanna. So if you're a student, you can access this software completely for free. To get the student competition bundle, you do have to do a little bit of paperwork to demonstrate that you're on a real competition team and to say, here's who the team members are. There are a couple of licensing options, so there can be some lead time associated with setting that up. The student competition bundle includes all of the packages that are listed here, including not just Atoms, but Atoms Car, Romax, that kind of thing. Dytran is another one. Apex Generative Design. If you want to have more rapid access to our software, any student, even if they're not on a competition team, can get a student edition. These are free versions of our software, again, available for students and for professors. They're typically limited in some way. So for Finite Element, they can only go up to 50,000 nodes, which is fine for practice learning purposes, but not very much for real work. So I would say if you're on a team, go ahead and apply for a student competition bundle, but you might want to sign up for a student edition also. If you want to follow up with us, we have a homepage for the webinar on SimCompanion that can give you links to other recordings and supplemental files. Like you'll be able to find the geometry files that I used for my demos there. We post our recorded webinars on YouTube, and you can follow me on LinkedIn for updates on this and for other ways that we're engaging with academia. Thank you to Joanna and Leonard for participating, and thank you to everybody who came to watch this webinar. I hope that everybody's found it helpful. All right, have a great day. Bye.